So we're going to work on simple and compound interest. This is going to lead into a discussion of a different exponential function. For right now, this is another example of things you can do with exponential functions. We mentioned that they're also applied to population growth, growth in computer speed, exponential decay is something you'll see when you work with radioactive carbon decay and, for instance, dating historically old items. This is the formula that we're going to need for our next application, which is compounded interest. So this one right here, depending on the fortunes of the maize and blue, maybe I'll give that formula to you on your next test. Of course, the more Michigan wins, the more you win. Yay, good deal. All right, just kidding on that stuff. What's this formula doing for us? It's calculating the amount of money you're going to get back if you invest some money into a bank account and you get interest compounded every now and then. Now, there's a few terms that are worth noting. A is the amount that you're going to get back. P is the amount that you put in. That's your principal. R is the rate of interest. And the thing that you need to note here is that it's as a decimal. So, for instance, down here in our first example, if we have R as 2%, you're not going to put 2 into the formula. What are you going to put in? 0.02, very good. So that's what's going to go into the formula. If you put in a 2, you're accidentally telling your formula that, oh, I'm getting 200% interest on my investment, which would be outstanding. If you find such a place that you get 200%, let me know. I'll give you extra credit. All right, but it's probably unlikely. Let's see what else. Principal and is the number of times of year that interest is compounded. So how often do they add interest to your account is really what that is. And then, of course, T is time. So let's practice with that formula, filling it in for Jackie's Junk Bond Bank here with an initial investment of $5,000 at 2%, which is probably pretty decent right now given our economic conditions. Plugging this all in, it would look like this. Now, it's going to depend on your calculator as to what you need to do with the exponent here. So I would suggest we just type this in as is and see how it goes. If you need to make some adjustments, let me know. I'll try and help you out with your calculator. The key is not to press the enter button until you're all done. So 5,000, parenthesis. You do not need to hit the times key because it understands that you're multiplying things. 5,000, parenthesis 1 plus 0.02 divided by 4 raised to the 4 times 3. Now, if you can look at that and go, oh, well, that's 12, that's fine. Some of you, if you got a really old calculator, it's going to give you problems if you try and enter it like this. This one works out fine. 5,308.389, etc. We're assuming in problems like this that this is money. So if you're talking about money, well, we don't have units of currency that go all the way down to the 9 here, or the 5. Where does our unit of currency stop? At the 8. Good. So we were on a round to the nearest hundredth on all your money problems. So this would be approximately $5,308.39. Thank you, Kaneem. Cool. Let's try a different one and see what happens when we change a few things. But are you able to get this number off your calculator? Is anyone struggling with that? Because I mean, this is a couple easy points that I want you to get on your exam. Let's move over to Sam's savings and loan. Sam's going to invest for the same 3 years that Jackie is. The rate of interest is a little bit less. It's 1.97, so that it'd be 0.0197 as a decimal. It makes a big difference if you convert that to a decimal or not. In fact, if I look back here at my previous problem, if I forget to put that as a decimal, check this out. My $5,000 that I invest for 3 years becomes $65,000. Wow, that's pretty cool. I guarantee, as much as I love teaching math, I'd be retired if I could do that kind of magic. All right, that's pretty special to multiply your money by 13 in 3 years. Woohoo! See ya. All right, now stranger than fiction. When I think of daily, I think of the number of days in the year. I think of 365. When banks think of daily, it's 360. Daily interest, this is no joke, daily interest when you compound it at the bank is N equals 360. So if we're investing at Sam Savings and Loans, yeah, he's compounding interest more often, but he's giving less interest rate. So are you going to get more than we did at Jackie's Junk Bond Bank? Well, let's find out. Here it is. Try and put it in. If you need to, you can do this separately. 3 times 360 is 1080. So every now and then you'll hear people like at the Olympics in the snowboard competition, they'll do a 1080. That's basically turning around 3 times. So, and in fact, in the most recent Olympics, I heard somebody doing a 1260, which is 3.5 times. Guy started forwards and he ended up backwards. And he landed it. It was amazing. All right, so let's take a look at how this one shakes out. 5,000, parenthesis, 1 plus 0.0197 divided by 360 raised to the 3 times 360 power. How do we do? Well, about $5,304. What would I round that to? 40. And I like that you gave me a 40 and not a 0.4. There needs to be something in the hundredths place. 0 or not, doesn't matter. So, okay. Well, it looks like the higher interest rate is better than compounding more often. But, you know, there's a trade-off. And both of these things have their effects. The goal here, at least initially, is for you to get comfortable with this formula and calculating with it. So, are we good there? All right. Thank you. Sam?
Where'd you get Jackie's Savings? Where'd you get that from?
Interest is compounded quarterly. So quarterly would be once every, 3 months or 4 times a year. Yeah. Yeah, compounded quarterly. Right there. So it's not stated as explicitly as compounded daily is 360, but it's implied. So if I compounded monthly, then what would n equal? 12. All right, so let's kind of go to an extreme example. And we're going to talk about investing in a very strange way here. If you ever see the old movie Trading Places, they have a standard bet of $1. Yeah, $1 is their standard bet. So let's invest a hypothetical $1 at 100% interest rate. Woohoo! Again, extra credit if you can find me a place that I can get 100% interest for 1 year. Now, 100% as a decimal is what? 1. So basically, I'm making everything in this formula on the right-hand side equal to 1, except what? What's the only thing that I haven't set equal to 1 in this formula? One more time. Any guesses? Any guesses at all? What haven't I set to 1? Yeah, the thing is there. Also known as an n. Yeah. So the only thing I haven't set to 1 is the n. Uh-oh. There we go. Let's zoom out a little bit. So let's play around with this kind of investment and see what effect compounding a different number of times a year has, just so you can understand a little bit better about compound interest and how it works. So we'll start out here, and here's our formula once we set everything equal to 1. The only thing we haven't figured out is n, and we'll do that here. If you compound once a year, that means you're going to get interest at the end of the year. January 1, You invest your dollar. End of the year, you got 100% interest. 100% of a dollar is a dollar. So you add it to your account, you got $2 now. Yay, great, you've doubled your money. But what if you compounded twice a year? So that means on January 1st, you invest your dollar. On July 1st, they give you half of the interest. So 50% of a dollar is 50 cents. They add that to your account. And the cool thing with compounded interest, the magic that Einstein said makes compound interest the most powerful force in the universe, is you get interest on your interest. You've got $1.50 in your account. At the end of the year, you get 50% interest. What's 50% of $1.50? I didn't expect a lag in the conversation here. 75 cents, yeah. Half of $1.50, 75 cents. Added to your account. Brian feels sheepish. He's like, oh, yeah, I should have known that one. So, added to your account is $2.25. So, cool. $2.25. And look what happened. By compounding more often, you got more money back. You got more interest on your money. Now, the rest of these are kind of filled in a little bit for you. If you compound quarterly, that initial dollar is going to turn into $2.44. Or monthly, $2.61. And hey, this is a fun game, right? Keep going. Sure, let's go up to what the banks consider daily interest. Now it's $2.71. Can anyone imagine, not the number, but what word would go along with compounding interest 8,760 times a year? Hourly. Every hour you're going to drop interest into your account. So, cool. But if you notice something is slowing down, here I got an extra 19 cents, then an extra 17 cents, then an extra 10 cents. And wow, look at this. Jumping from 360 to 8,760, I didn't even get an extra half penny in interest. So it's slowing down. Now, through the magic of calculus, you can actually drop infinity into this formula. And what that would show you is you get this magic number back in terms of interest. 2.71828182845, whatever. All right, keeps on going forever. And that number is E. And I want you to find that number on your calculator. So E, you can find it in two places, at least on the graphing calculator. On the graphing calculator, you can find it right above the division key. So second, and then E, and you should get something like this. All the digits that I just had up there. Almost all of them. So nice. There's also another place that you can get